Okay, we're now in section 16.5, capacitors. We're starting to get into electrical circuits, or this is certainly one of the components in electrical circuits. So, capacitor. A capacitor is a device used in many different electric circuits, for example, to tune the frequency of radio receivers, eliminate sparking in automobile ignition systems, or store short-term energy for rapid release in electronic flash units. When you take a photo and you're using your flash, you'll notice that there's like a little light that says wait before you take another photo. What it's doing is charging the capacitor for the next flash on your camera. The figure shows a typical design for a capacitor. It consists of two parallel metal plates separated by a distance d. In a circuit, the plates are connected to the positive and negative terminals of a battery or some other voltage source. When this connection is made, electrons are pulled off one of the plates, leaving it with a charge of plus Q, and are transferred through the battery to the other plate, leaving it with a charge of minus Q, as you can see in the figure. The transfer of charge stops when the potential difference across the plates equals the potential difference of the battery. So you can see that a charge capacitor is a device that stores energy that can be reclaimed when needed for a specific application, such as storing the voltage needed to light your flash on a camera. Okay, the capacitance C of capacitor is the ratio of the magnitude of the charge on either conductor or plate to the magnitude of the potential difference between the plates. In this equation, the quantities Q and delta V are always taken to be positive. Let's do a quick example. Well, let's go back to the equation. So C is defined as the charge divided by the delta V, the voltage difference. The SI unit for capacitors is coulombs per volt. Let's do a quick example. Say a 3 millifarad capacitor is connected to a 12-volt battery. Using our equation, we find the magnitude of the charge on each plate of the capacitor is 36 microcoulombs. From this equation, you can see that large capacitance is needed to store a large amount of charge for a given applied voltage. The farad is a very large unit of capacitance. In practice, the most typical capacitors have capacitances ranging from microfarads, 10 to the 6 farads, to picofarads, 10 to the minus 12 farads. So microfarads, 10 to the minus 6 farads, and picofarads, 10 to the minus 12 farads. You'll see those quite often. We'll see them in the lab when we go into the do the next laboratory experiment. The capacitance of a device depends on the geometric arrangement of the conductors. The capacitance of a parallel plate capacitor with plates separated by air, as shown in the figure, can be easily calculated from three facts. First, the magnitude of the electric field between two plates is given by the relationship E equals sigma over epsilon 0, where sigma is the magnitude of the charge per unit area on each plate. Second, the potential difference between two plates, delta V, where D is the distance between the two plates. So delta V equals ED, the E field times the distance. Okay. Third, the charge on one plate is given by this relationship where Q is equal to sigma A, where A is the area of the plate. Let's substitute into the definition of the capacitance. C equals Q over delta V equals sigma A over ED equals sigma A divided by sigma over epsilon 0D. Now let's cancel the charge per unit area sigma shown in this equation, and we get C equals epsilon 0 area over the distance. That's the area of the plates divided by the distance D. Here we have our result where A is the area of one plate, D is the distance between the plates, and epsilon 0 is the permittivity of free space. From our result, you can see that plates with larger area can store more charge. The same is true for a small plate separation D, because then the positive charges on one plate exert a stronger force on the negative charges on the other plate, allowing more charge to be held on the plates. Okay, this figure shows the electric field lines of a more realistic parallel plate capacitor. Notice that the electric field is very nearly constant at the center between the plates, but becomes less so when approaching the edges. In general, we can assume the field is constant throughout the region between the plates. This looks very much like the section that you were supposed to draw in your field and equipotential lab from last Thursday, I believe. Okay, computers use capacitors. For example, one type of computer keyboard has capacitors as the basis of its keys. As you can see in the figure, each key is connected to a movable plate, which represents one side of the capacitor. The fixed plate on the bottom of the keyboard represents the other side of the capacitor. When a key is pressed, the capacitor spacing decreases, causing an increase in capacitance. External electronic circuits recognize each key by the change in its capacitance when it is pressed. Another practical device that uses a capacitor is the flash attachment on a camera. A battery is used to charge the capacitor, and the stored charge is then released when the shutter release button is pressed to take a picture. The stored charge is delivered to a flash tube very quickly, illuminating the subject at the instant more light is needed. Another example of using capacitors is on the forefront of fusion research for what is called electrostatic confinement. For what is in this role, capacitors discharge their electrons. Get away there! There's a cat approaching me. In this role, capacitors discharge their electrons through a grid. The negatively charged electrons in the grid draw positively charged particles to them, and therefore to each other, causing some particles to fuse and release energy in the process. Okay, these are the symbols for the capacitors. The symbols shown in the slides are commonly used to represent different elements. The positive terminal of the battery is at the higher potential and is represented by the longer vertical line in the battery symbol. That's the one in green. In the next topic, we will discuss a circuit element called a resistor, which is represented by the zigzag line here. Last is the symbol for a light bulb. Wires, by the way, are represented by straight lines. So from top to bottom, we have a capacitor. Notice how the blue lines, they're of the same distance. The battery one is larger than the other. The longer line is the positive terminal, the smaller line is the negative terminal. And the resistor is a zigzag line. And the light bulb, it almost looks like a little light bulb. Okay. 24. Yeah, this is the last slide. The figures show a real circuit and its schematic diagram. Let's trace the path of the real circuit to see that it is equivalent to the diagram. Start at the positive terminal of the battery. We come first to a junction with a light bulb. If we follow the path through that bulb, we encounter a resistor, and if we follow the other path, we encounter another light bulb. Both paths reconnect and end up at the negative terminal of the battery. Okay, this ends this section. The next section we'll cover is 16.6 combinations of capacitors, where we'll learn about capacitors in parallel and capacitors in series.